Hello everyone, welcome back to the course. We are just starting week 8. My name is Ajad Islam and I'm going to be your instructor for this week. This is lecture 15 and in this lecture there are two parts. In the first part we are going to talk about orthogonal and orthonormal basis of a vector space, and in the second part we are going to talk about how to convert any basis of a space into an orthonormal basis. So this is a fairly easy lecture, I would say, and pretty important too. So let's get going. All right. So what is exactly the basis of a space? Now, we have talked about this over and over in our past weeks, but I'm just going to give you the definition one more time. So the basis of a space is going to be a set of vectors, but the vectors have to be linearly independent. That is condition number 1. And condition number 2 is those vectors have to span the entire space. So if we get those two conditions fulfilled, if we get some vectors that are linearly independent, which means there is no redundancy, so we have got those vectors, and if those vectors can span the entire space, then we can call that set a basis of that vector space. Alright, so that is the basis of a space. What do we call an orthogonal basis of a space? So if the vectors inside the basis, so a basis is a set of vectors, right? So if each vectors of that set are perpendicular to each other, we call that an orthogonal basis. So the term orthogonal actually means perpendicular. So if we have some vectors, let's say v1, v2 and v3, if v1 is perpendicular to v2 and v3, similarly v2 is perpendicular to v1 and v3, and so on, we can call that basis an orthogonal basis of that space. Now we have orthonormal basis. Orthonormal basis is basically orthogonal basis with only one additional property. So just like orthogonal basis, we have the vectors inside the basis, and they have to be perpendicular with each other, all of them. And the additional property is the length of each of the vectors of the basis has to be 1. So if we have that property fulfilled, we can call that basis an orthonormal basis of a space. Now, a very common example of that is the standard unit vectors, which create the basis of R2 or R3. Let's take R2. We have for R2, we have the two basis vectors, the standard basis, which is made of two vectors, I hat and j hat. Now we already know I hat is perpendicular with j hat, and the length of I hat is 1, length of j hat is 1. So we can say that the standard basis is an orthonormal basis. Similarly, for R3, we have I hat, j hat, and k hat. All of them are perpendicular with each other. The length of each of these three vectors are 1. So we can say that this basis is also an orthonormal basis. All right, so the definitions are out of the way. Now, we also know that each basis of a space, let's say you have a space, we know that each basis for that space is going to give us a coordinate system. Each basis will have a different coordinate system. I'll show you what I mean. So this is the two-dimensional space. Let's call it R2. We have the real two-dimensional space, and let's say these two vectors create one of the bases of the two-dimensional space. Now, we have already seen this earlier, and if you recall in one of the assignment questions, we showed that the choice of the basis is what determines the axis. So as we have these two vectors, our axis is going to be like this. We have one axis that will go along this vector. We have the other axis that will go along this vector. And as you can see, the two axes is going to determine the coordinate of any point in this plane. So let's say we have this point, and the coordinate of this point, if we have this basis, is going to be something like this. So x along this axis and y along this axis. So the coordinate is x, y. Now this coordinate is completely dependent on the choice of basis. If we chose a different basis, let's say if we chose this basis, please note here that these two vectors inside the basis are not perpendicular to each other, so they are not orthogonal or even orthonormal. They are just a normal basis. So if we chose this basis, they could still span the entire R2 space, but the coordinate that these two vectors will produce for this same point is obviously going to be something different. So the coordinate for this point is not going to be xy. This is going to be something different. Let's call that x new and y new. All right, so this is a different coordinate. So the point here is the coordinate system is determined by the choice of basis. All right, so now let's talk about, as we have shown you how the coordinates work according to the basis, let's talk about why we prefer the standard basis vectors, which is orthonormal, or in other words, why we prefer orthonormal basis over some other basis like this one, which is not orthogonal or orthonormal. So I will show you a couple of examples. So first of all, think of the magnitude of a vector. We have this vector v, and according to our standard basis vectors I hat and j hat, let's say the coordinate of this vector is xy. So we know the magnitude, the length of this vector is going to be x squared plus y squared, right? This is a very easy formula, and we can use it to determine the length of any vector in any dimension. Now let's see what happens if our basis, two basis vectors, were not perpendicular. If we had two bases which were like this, two vectors which were like this basis is obviously not orthogonal because this is not a 90-degree angle, right? So as you can see, this relationship does not hold anymore because this relationship comes from the Pythagorean formula, which relies on the 90-degree angle here, which says the length of this square plus the length of this squared is equal to the length of this squared. So we get the formula from that. But as you can see, the same formula does not apply here. So if we used a different basis than our standard orthonormal basis, like something like I hat and j hat, which is orthonormal, if we had used a different set of vectors as our basis, calculating the magnitude of vectors would have been much more complex and difficult. I think you can appreciate that from this figure. All right, so let's look at another example. So let's look at the dot product of two vectors. So we have our vector x with the coordinate x1 and x2. We have our vector y with the coordinate y1 and y2. So the dot product of this, as you can see, we can, if we use the standard basis vectors, I hat and j hat, they are orthonormal. This is an orthonormal basis because I hat and j hat are unit and has a unit length and they are perpendicular. So if we do the calculation, we ultimately end up here. The dot product of these two vectors is just going to be x1 y1 plus x2 y2, because this becomes 0 because j hat and I hat are perpendicular, so the dot product here is going to be 0. I hat and j hat is going to be perpendicular, so cos 90 is equal to 0, so this is going to be 0. This dot product is going to be I hat and j hat. I think I have made a mistake here. Oh no, these both are j. So two have the same direction, so this is cos 0, which is 1. So ultimately we get here. You already know how this works, so I don't know why I started explaining that. All right, but if our basis vectors were not I hat and j hat, if they were something different, we wouldn't be able to eliminate this, because we could eliminate this because we know I hat and j hat are 90 degree. They are orthogonal. So this is going to be 0 because the dot product of two 90 degree vectors are going to be 0. But if we did not have a basis, if we used a different basis than I hat and j hat, which was not 90 degree, let's say something like this, they are not at 90 degree angle with each other. So the calculation, we wouldn't be able to write 0 instead of this, so the calculation would be much more complex and this formula would not hold anymore. Alright, so this formula would not be correct for any basis which is not orthonormal. So this is one more convenience we get from orthonormal or orthogonal basis vectors. Alright, so another example, finding coordinates. So let's say we have the vector here, the same vector I just drew 2 copies of it. We want to find the coordinate of this vector. Now, if our basis is 90 degree, that is orthogonal, as you can see, the coordinates are going to be this and this, right? And these are just the projection of this vector onto the 2 bases, two vectors of the basis. So this coordinate is going to be the projection of the vector onto this base, this vector, and this coordinate is going to be the projection of the vector onto this vector, right? Very simple, very easy. The same cannot be said for this one. To calculate the length of this, we cannot just take the projection because the projection is going to be 90 degree. So the projection is going to be something like this, and the projection here is going to be something like this, which will not give us the 2 coordinates. So finding coordinates of a vector, if we are using a basis that is not orthogonal or orthonormal, is much more complicated than if we are using a basis that is orthogonal. Now, this is a very good example which also shows us why simply using an orthogonal basis is less convenient than using a basis which is not just orthogonal but also orthonormal. And let's see that in our next slide. So as we saw, to find the coordinate, we are going to take the projection of this vector onto this vector. And to find the coordinate, this coordinate, we're going to take the projection of this vector onto this vector, right? So this is the formula of projection. We have already, I hope you remember this formula, you have already seen this in week 7. So I'm not going to go into the details of the formula. So the projection of x, let's call this vector x, onto b1 is going to be x1 dot b1 divided by the length of b1 into the vector b1 itself. Now, if the length of b1 and b2 is arbitrary, if they are not 1, you have to calculate this, right? But look what happens if this is an orthonormal basis. If the length of b1 and b2 were both exactly 1, you wouldn't have to calculate the length of b1 because this is just 1. So the projection of x onto b1, let's call this vector x, onto b1 or b2 would be a much more simple formula because the length of b1 is 1, so you don't have to divide by anything. So that is why we use an orthonormal basis as our standard basis vector. Alright, so I think by now you are clear about what is the basis of a space, what is an orthogonal basis, when we can call a basis orthogonal, also when we can call a basis orthonormal. I hope you are clear about that at this point. We also showed you a couple of examples that highlights the significance of using an orthonormal basis, why it is more convenient for us to use, and that's it pretty much. You just need to kind of appreciate the fact that orthonormal basis works much more elegantly than a normal basis. So that would be it for the first part of this lecture. Thank you, and in our next topic we are going to see the Gram-Schmidt process, where we are going to convert any given basis of a space into a basis which is orthonormal. Alright, until then, thank you.